I'll not tell you how to do percolation, I'll just analyze it. All right, thanks a lot for being here. And it was a great opportunity to kind of talk to you people. And so, yeah, today I'm going to talk about subcritical percolation on evolving networks. Well, these evolving networks are sort of different from what you've seen so far. And this is joint work with my colleague Shankar Bhamidi at UNC, Remco, who is here, and Ronak Ray from Brown. All right, so a little bit about the classical percolation on static random networks. So what I call static are networks where you have a set of vertices, fixed set of vertices, and then you throw in edges according to some, and everything else being small. So there is this very sharp transition, and at the critical window, things are harder, right? So if you look at the critical percolation probability, you fix P at that, you see that the maximal component is of order n to the power 2/3. And if you zoom in the critical window, so think about the case with Erdős-Renyi. So again, all of you know the definition by now. So think about P as the probability of the edges. So this is again G and P. And you take P to be 1 over n, which is the critical threshold. And then you kind of perturb this by lambda times n to the power 4/3. So you kind of vary, think about a large n, and then you vary lambda now. And what you do is, so we know that the maximal component is of order n to the power negative n to the power 2/3. So what you do is you order the components. So let's call this so parameterized by lambda. So this, you order the components, the largest one, then you take the second largest one, and so on. So you can order the components, rescale them, and then you look at sort of its limit as n goes to infinity. And there is a seminal work by David Aldous which says that this sort of converges to a process called the multiplicative coalescence. So it will converge to a process like this. You note that the n is gone now. And so on. So this is an infinite dimensional process on some L2 space where you order the coordinates. And as lambda varies, these components will evolve in a certain way. And as lambda grows, well, P increases, right? So the components will merge, and component I and component J, so they will merge to they will merge to give you a component of this size. Ij at rate the product C1 lambda times C2 lambda. So that's the dynamic. So components will merge at a multiplicative rate, and this keeps going on. Okay. So that's called the multiplicative coalescent. And these components, so you can also view these component sizes as sort of ordered excursions of a Brownian motion with parabolic drift reflected at 0. So all of these go back to Aldous' seminal paper. Okay, so why am I talking about this? I'm not going to talk about static networks. I'm going to talk about dynamic networks, where the network itself grows in vertex size over time. So vertices keep arriving sequentially in discrete time, and they attach themselves to the existing network according to some rule that I'll talk about. Now, what this creates is a lack of exchangeability. Okay? So vertices have their edges, and the attachment also kind of depends on the geometry of the existing network. So there is lack of exchangeability and also long-range dependence. So a vertex that suddenly grows in size or degree will tend to keep growing faster. So those will be my networks, sort of the rich get richer kind of things. And that will create these sort of long-range dependencies. And the question is, what happens when you sort of perform percolation on graphs like that? So the model is this. So you start with one vertex. Each vertex comes in with a fixed number of out edges. And each edge connects to the existing network, say to a vertex V in the existing network, with probability that's proportional to that quantity. So A times the degree of V in Gn plus some offset delta. So the degree will kind of reinforce, so rich get richer. But also, if that A is 0, that's also a model, a perfectly valid model, where the older vertices have an edge because they have been there for longer. So there is always this sort of correlation between degree and age, regardless of whether A is positive or A is 0. So this is the network. So the model is you grow the network to size n, and then on that you percolate each edge independently with some probability path. And for A greater than 0, this is called the preferential attachment model. For A equals 0 and delta greater than 0, that's called the uniform attachment model, or the random recursive graph. Mm-hmm. That's correct. I mean, you could also view it in the same fashion. So, yeah, you could also kind of co-percolate with the growing network. Yeah, that will give you the same realization, or the same distribution of the realization. Is the model clear? Oh, there is a question.
I was just curious. So here A is either 0 or positive. Could there be a case in which either A was negative or we were like inversely proportional to the existing degree, trying to sort of make it not rich gets richer, but trying to allocate edges where there are few?
So there are models like that. And I think it's called anti-preferential attachment. Okay. And I think Antur Bandyopadhyay, who's not here, he is an expert on these things. But yeah, so that's a very interesting model, but that's not the model that I'll focus on here. So here there is correlation that's positive with age. There will be negative correlation with age. But yeah, for this talk, in fact, you'll see I'll focus on A equals 0. So that's the simplest model. All right, so what do we know about percolation on these graphs? Not much. There are some conjectures, so statistical phase conjectures. So in the early 2000s, there was this well-known conjecture called the BKT phase transition. And what the conjecture says is, so pi c, you have to figure out what pi c is for each of these models. But once you figure that out, and you slightly grow beyond pi c, you will see an emergence of a giant component, but in a very smooth way. So what do I mean by that? So think about this as sort of C max. So this is the maximal component divided by n, and this is your pi. So there is some pi c. So in static models, what you see is so in the limit, so this is the limit of n. So this limit is 0 till here, and then you see something like this. So it's continuous but not differentiable at this pi c. So the first transition that was conjectured for these models is that this thing happens in a smooth way. So this is the classic example of that bump function which is smooth at the transition point. So that's why this transition happens very smoothly. So that's the content of the first conjecture. And the second one, it says that, okay, so if you look at pi less than pi c, so in the subcritical regime, somehow things look like the critical window in static models. So for any pi less than pi c, there should be some exponent that depends on pi, such that the largest component is not log n, it's n to the power alpha pi. So these are the two conjectures. And again, like these are the sort of like the authors who kind of propose this. And here alpha pi is less than half. Now, what do we know mathematically? Well, the BKT transition has been almost successfully resolved by these papers, Bolobos, Janssen, Riordan, Bolobos, Riordan, Duret, Derek Motors. So for a variety of the models I discussed, so they have exhibited the smooth phase transition that I told you about. Yeah.
T-type
Yeah. So I think the statistical physics models, like the general models, are more complicated. But I think these papers, so they actually don't deal with the general model. They deal with models in the sort of ballpark of what I mentioned. So there is no Hamiltonian, but there is sort of like these UA and PA type models, and there are sort of inhomogeneous random graph analogs of these. But yeah, so I'm not claiming that the general conjecture is resolved, but some cases, including the case that we have. All right, so what do we know about the subcritical regime? Well, not much. So even for the UA model, that will be kind of the star of our show today, where A equals 0, all we knew so far is that the maximal component is of order root n log n. And this is again by Bolobash and Riordan. And there are variants of this model. I told you there is this thing called the inhomogeneous random graph analog of PA. So I don't want to discuss that in detail. So there are variants of this model for which like something like this has been shown. So log Cmax n divided by log n, that converges as n goes to infinity almost surely to some beta pi. So this is weaker than what I conjectured, or not what was conjectured here. So proving this will show this, but showing this will not necessarily prove this. This is at the logarithmic level. And also the models are different. So again, so there is a sort of a variant of the model that I discussed where you see this as an inhomogeneous random graph, which kind of gives you the same degree profile as preferential attachment, but somehow it becomes more tractable. So I kind of treat that as a black box for now. All right, so our goal will be to understand this case, the second point, okay? And try to understand what the maximal components, sizes are, and how they evolve. Questions so far? All right, so now let me tell you a little bit about why you would expect something like this picture to show up in the whole subcritical regime for these models. Now, again, like think about, so the original model is in discrete time, but think about a continuous time variant of this. So all that changes is instead of vertices coming at times 1, 2, 3, and so on, vertices come in at epochs of a Yule process. So if your whole network is size n, the next arrival happens at rate n. So that's called the Yule process. So it's a continuous time arrival, and once the vertex arrives, it attaches according to the same mechanism. So it's not a big leap in understanding, it's just a convenient restatement of the model. So for that case, you can actually track the evolution of components. So think about two components at time t, CA and CB. Now, when a new vertex comes, so think about just n equals 2 for now. Okay? So each vertex comes in with two outgoing edges. Okay? So if those two edges connect to CA and CB, and they're both percolated, then these components merge, right? So they merge to CA plus CB plus 1 at this rate. You can compute the rate, so this is the rate, and note that here you see a multiplicative rate, right? So this is one case. Other case could be, okay, so both the edges or one of the edges, so the vertex only connects to one component. In that case, the component increases by size 1 or increases by unit 1. And the third possibility is, well, the vertex comes in, both its edges are unpercolated, so it's a singleton for now, it will create its own component. So these are the three possibilities that could happen at every arrival. And the first thing is the highest probability event in some sense. And that's what should ring a bell as we see here, right? So the first point is more like the multiplicative coalescent kind of evolution. So that should kind of intuitively suggest that you will see something like a power law behavior, like a polynomial in behavior of the maximum component. All right, so that's what I have here.
I have a question. The CAT is the component size of the open edges, is that right? Or
Yeah, so open, yeah, the one that happens with probably pi. Yeah. I keep confusing open and close, but yeah, the ones that exist.
Exist.
Yeah. Yeah. So for most of the talk, I'll talk about the uniform with n equals 2. And we are working on sort of the more general case, but the ideas that you'll see here do actually extend for the more general. All right, so I'll state our main result. So the pi c for the uniform attachment model with n equals 2 was already like sort of figured out by Bolobash and Riordan 2005. It is this number, 2 minus root 2 over 4. So once you have this, for every pi less than pi c, define this number alpha pi. Well, it's some function. It's not the nicest function, but it's some function in pi. So our main result is, for any pi less than pi c, if you look at the component containing the ith vertex, if you rescale it by n to the power negative alpha pi, it will converge almost surely to a possibly random limit. So again, we don't know what this limiting random variable is, but we know that there exists a limit. And moreover, a similar kind of asymptotics will hold for the maximal component. So with the same scaling, it will converge, and we also know that the limit is going to be the maximum of these limits. So it's like an interchange of limits kind of argument. And thirdly, so this is again a separate part, there is something called weak persistence. And there is some memory, right? So the older vertices have an edge. We see that the older vertices also have an edge in terms of their component sizes. So this sort of statement says that if you look at the maximal component, then the probability that it is a young component, that is, its oldest vertex is at least I or more, is less than epsilon. So for any epsilon, you have a k epsilon for which this holds. Yeah.
In the first part A, you're looking at the component size at time pi, is it?
No. So this is this is in discrete time now. So
Yeah.
look at the network of size n,
Very good, yeah.
and then look at the sort of component containing vertex I
Yeah.
in the network of size n. We scale it, and that's as n goes to infinity, that's the limit.
So you have Ci pi of pi, that's what I'm asking. So
Oh yeah, so there will be also pi here. So the limit will also, okay, so we don't know whether the limit depends on pi,
okay.
but there is some limit, possibly depending on pi. Oh yeah, that is a typo. This
yeah.
in n.
That's and that's what I'm asking. Yeah. So
Sorry.
that's why I said time pi. I was confused by. Yeah.
You always find my typo, Shiva.
That's not true.
What was that? No, they're not independent. Absolutely not. Again, we don't know how to prove that, but I mean, clearly, I mean, hopefully they're not independent. Yeah. I mean, yeah, it's.
They're also not giant components, right? Because they're scaling differently.
Sorry?
They're also not giant components because
By giant, you mean order of n size?
yeah.
No.
No,
So
they're
large,
then smaller. Yeah. Okay.
yeah. So it is what I said
Yeah,
before.
of
Yeah.
course.
Alpha pi is less than half. I think I wrote it somewhere.
Yeah. It's 1 minus and 1/2.
Yeah.
Yes.
There.
Thank you.
The questions? All right. So this is what happens at the sort of maximal component and sort of fixed I component level, right? Now, one thing I should mention, like this is something that's haunted me over time, is that these preferential attachment type models have two distinct regimes. So if you look at the evolution of the older vertices, there the degrees are growing like n to the power something, right? So that's like a denser part of the same graph. But if you look at a uniformly chosen vertex in this graph, there, if you look at a neighborhood around that, things look very sparse. The degree of that is order of 1. So this is the lack of exchangeability that gives rise to these two different regimes sitting inside the same graph. So this is kind of answering what's happening at this global scale, like the maximal component and the component containing the root, vertex 2, or so on. So now let's talk about what's happening to a typical component. So pick a vertex uniformly at random and look at its component. Okay, so these are some pictures. So these are, so this is, in this case, these are the first 6 components, and this is the maximal component. And you see that these look kind of like trees. Right? So there are small loops, which you don't see here, but you don't see big loops. Okay. And I say that we don't know what the limit zeta I is. but these are some sort of KDE plots. And these kind of suggest that things can't be constant, so they have to be random variables with roughly this shape. We don't know what the distribution is, but this is a simulation. Okay, so now let's talk about the, okay, so yeah, I'll get there. But 2 points I wanted to mention the following. So for static models, in the subcritical regime, maximal degree and maximal component, they correlate very strongly. So if the maximal degree is order of log n, like in sort of the sparse heterogeneity, it's very likely that the maximal component contains that maximal degree vertex. That's why, and they have a similar kind of scale. And similarly for the like configuration model, you have a story like that. But in the case for the UA that we are considering, the maximal degree is order of log n. But the component size is some polynomial in it. So there is again sort of this sort of separation between the maximal degree and the maximal component. And moreover, so in a previous work with Shankar, we showed that for the uniform attachment, there is no persistence of the degree. So the maximal degree vertex could actually be quite far away from the root. It will actually be at some distance, constant log n away from the root. So somehow this tells you that there is weak persistence. So the maximal component corresponds to an earlier vertex. The maximal degree will be some later vertex, possibly not in the maximal component. So there is this sort of like, so the maximal degree and maximal component sizes don't correlate as strongly. Okay, so now we come to something called the susceptibility, which is kind of going to give you the size of the component of a typical vertex. So consider this statistic of the network. So look at the k power of all the component sizes in the graph of size n and divide by n, right? So this is called the kth susceptibility. You can rewrite this by not summing over the components, but summing over the vertices and the components containing those vertices, okay? So these are the same thing. So so the second formula kind of tells you, so this is like, you pick a vertex uniformly at random, and you look at the k minus 1 power of its component. So that's the sort of k minus 1 power size of a typically chosen vertex. Now when k equals 2, this gives you the average size of component of a uniformly chosen vertex. Now this is a local quantity, right? So it's a quantity of a typical vertex. It's a function of a typical vertex. But somehow this really governs the global growth of the component. And sort of the main connection between them is the following. So again, I'll make this rigorous in the later slide. If you look at the evolution of the log of the component containing the root, then the sort of growth rate of this is proportional to the second susceptibility. So although the component of the root is a global quantity, its growth rate depends on a local quantity. So there is this sort of global to local connection. All right, so the second result is it says that, okay, consider the UA with m equals 2. For pi less than pi c, the second susceptibility, which is again the size of a typical component of a typical vertex, will converge almost surely to a number which has this explicit form. So for a fixed pi, you get this limit. And note that this limit is again finite, right? So you don't have any scaling. So look at the component of a typical vertex, it's order of 1. And as n goes to infinity, it converges to this explicit number. So sort of zooming out, so the maximal component grows like n to the power alpha pi. A typical component size approaches this number. So that's again showing you that there are two regimes, the typical and the global, they behave very differently. Now this is again, okay, another point to note, which is again a very important point, is that if you take a limit of this number as pi increases to pi c, the limit is finite. So as you approach criticality, the size of a uniformly chosen component, a vertex component, remains bounded. And that's in stark contrast with the static model where it actually blows up like this. So this is also kind of pointing to this smooth phase transition here. So if you're approaching phi c from the left, you don't really see what's happening on the other side. Things are kind of very smoothly sort of kind of blending into supercriticality. So questions?
I mean, what sort of smoothing are you doing in this dynamic? You must be doing something. Are you merging components a little too quicker, or
Sorry,
is that this differentiability is happening in the theta p curve, right? Or
yeah,
out,
yeah.
and the fact that the static model blows up and this goes to a finite blob, big blob.
Yeah.
Is it because you're merging components in some sort of a continuous way? Is it what's happening? Or why is it happening physically? Like, it seems almost like a similar thing, right? After the graph is formed, it's just the percolation of the graph, right?
Yeah, so again, so I don't think we have a clear intuition as to why the susceptibility remains bounded, right? I mean, it's just a miracle. It's like so we don't really have a very physical handle on why we are seeing this. I mean, Remco, do you agree?
There has to be something in the topology that makes this happen, and we don't know what it is. It's a bit of a strange.
An open edge and then collapsing to open guide.
I mean, we could try to make up explanations, yeah.
Yet.
Yeah.
Then apply percolation, so that it's something in the structure of the full graph. It's not the dynamics of the percolated thing, but we really don't know what it is.
So it is kind of, I mean, so the thing is, we were doing some calculations, and then it turned out that this is the formula, and then we kind of like reverse engineered and try to see why it's happening. Then we found the conjecture, and so yeah, I mean, yeah, that's the truth, that we could try to come up with a story, but we don't really have a story. All right, so these are the main results, and now I have like, what, 20 minutes, 15 minutes, 11 minutes? Okay. All right, so I was trying to sneak in the 5 minutes that I had. Okay. All right, so in those remaining 11 minutes, I'll try to give you a little overview of the proof. Okay, so don't get scared. So don't need to look at this. So I'm just trying to kind of formalize what's the growth rate of the component of the first vertex. Now again, we are in continuous time, so switch to continuous time, because now you can you have a continuous time Markov chain, and you have generators of this, right? That makes it a little more convenient analytically. So the rate of change of the component size of the first vertex, you can think of this as a drift part and a martingale part, right? And the drift part is given by sort of the generator of the Markov process acting on C1. And again, so you can write this down. So this is sort of the evolution equation corresponding to the generator. And forget about this, just look at the last line. So this tells you that, okay, there is a martingale part that I'm not showing you, but at the sort of level of the drift, the rate of change of C1, the root component, is this number times the size of C1 itself. So if you could show that this thing has a limit as t goes to infinity, and this thing goes to 0, then you can convince yourself that, okay, like roughly convince yourself that C1t will grow like e to the power this number times t. And once you show that, actually that's all, that we are there. Okay. And now the question is, how do you show it? Now note that this is not really a closed system, right? So you have C1 here, you have C1 here, but S2t depends on all the components. So this is not a closed equation. You have to kind of separately analyze this. And this we do by a stochastic approximation scheme. So what we do is we write down sort of the increment equation of S2 between n plus 1 and n. So you see that we are flipping between discrete and continuous time. And that's actually confusing. It's also helpful for the calculations. So in discrete time, if you go from size n to n plus 1, you can show that the susceptibility increment has this form. So it has some vector field that's kind of driving the first order behavior. There is an error, which again is bounded by the fourth susceptibility. And there is a martingale increment term, which has a quadratic variation bounded by this. So these are some estimates. But the point of this is, if you could analyze the behavior of this and analyze the fixed points of this, that would give you possible candidate limits for the susceptibility. So that's the stochastic approximation scheme. And okay, so what we see is, so the f is actually a very simple function. It's a quadratic function. So I'll just draw a picture here. I'll draw this here. So the function looks like this. This is your f. So it has two zeros, lambda 1 and lambda 2. And think about s sort of moving on the x-axis, right? Now that this is the stable region. So this region is stable. So if your susceptibility gets stuck in here, it will actually slowly gravitate towards lambda 1. But now, if your susceptibility goes here, and the martingale term is not strong enough to bring it back to the stable region, it will diverge to infinity. So that creates a technical problem. We don't, so okay, we can guess that this is the limit, but we don't really know, like we don't really have a simple proof of saying why it won't kind of visit the unstable region and drift off. So this is where we kind of appeal to something called this, wait, I think there is a slide. Okay, so, okay, I'll come to that. So, okay, this is where we come to sort of like, we have two estimates, so we appeal to something called free graph inequalities to first give a weak bound on the maximal component. So we show that the maximal component cannot grow faster than this, okay? So this is sort of a combinatorial way of controlling the moments of components, and this gives you sort of an a priori control on the maximal component. This will not prove any kind of like limit theorems, but it gives you some control on the size. And now let's come back to lambda 1 and lambda 2. So lambda 1 again has this form. This is exactly the limit that you saw for S2. And this is the unstable 0. Okay. So we somehow need to show that if you just track the susceptibility, right, as a function of n, it will keep kind of like jiggling around. It can't really drift off to infinity. It will keep on coming back here infinitely often. If you can show that, then you can show that, okay, it will converge to the 0. So again, like I only have like 6 minutes, so I don't want to go into the details. So what we show using the local limit. So this graph has a so you can actually write down a local limit description of the graph model. And using that, you can actually show that there is a convergence of the susceptibility in probability to a limit. And this limit is nothing but the component of the root in this infinite graph that corresponds to the local limit. So again, I'm like hiding lots of details, but you can kind of believe that, right? So the main challenge here is to kind of show that the component size of the root in the local limit actually agrees with your lambda 1. So once you have that, you have this limit in probability. And now we go back to the basics, right? If something converges in probability, there is an almost sure convergence of sequence, right? That just means that regardless of what you saw in the stochastic approximation, things will keep on coming back in a certain neighborhood of lambda 1. So after a geometric number of trials, you'll get stuck here because then the noise is not strong enough to kind of bring you out of that. The noise and the errors are small enough. So that kind of gives you the result. So, and we actually can upgrade the convergence from probability to almost sure using a combination of the local limit and the stochastic approximation. All right, so with that, again, let me go back to our formula. So the rate of change of the component size, remember this is like this. We know now that S2T converges almost surely to S2 infinity. And using this sort of a priori bound, this term is small, it goes to 0. Because again, alpha pi is less than half, so this whole thing, so the root, the max component grows like n to the power some half minus delta. So that's why this term goes away. And I mean, it takes a while to kind of formalize this heuristic, but you get sort of this kind of a behavior, approximate behavior, which tells you that the maximal component in continuous time is of this form. Now, going back to discrete time, you have expression like this. Sorry, there were a bunch of steps. I might have lost a bunch of you, but again, I can revisit this later. All right, so that's kind of the rough proof sketch. And then to kind of like upgrade this to the maximal component convergence, we actually prove the weak persistence first. And that requires sort of some concentration estimates using sort of higher moments of component sizes and some sort of semi-martingale decomposition. So these are things that you can kind of like, it's a long technical calculation, but it gives you what you want. So that kind of upgrades the sort of fixed degree convergence to the convergence of the fixed vertex convergence to the convergence of the maximal component. All right, so that tells you like about the first part. I know I have 3 minutes. So, okay, so now let's go to another result. Now, what about the general model? Okay, for the general model, we are working on it. We don't have the paper finished yet. But what we know, Rajat, Remco, and Ronak, they have a paper in 2023. They actually identify what pi c is for the general model with general positive A and delta. So there is this sort of complex formula, but there is a formula. So we have calculations to actually quantify exactly what alpha pi should be for the general case. And alpha pi looks like this. Again, the details are not important. There is a formula. And we have the same sort of meta theorem because we don't have all the details yet, but we are confident that this is the result. So you have the same kind of sort of limits, but now with alpha pi taking this form. So that's for the general preferential attachment. All right, so I still have 1.5 minutes. I'm there. So this is the last slide. So again, we saw that, okay, for these sort of models of evolving graphs where vertices arrive over time, you have this weird criticality in the whole subcritical window. And that's kind of a consequence of this long-range dependence that you see in these models. Now, this kind of phenomena has been sort of seen before where sort of the maximal degree and sort of like is different from sort of the global behavior in the context of something called page rank. So page rank is a centrality measure. And in some papers with Mariana, Olvera Cravioto, and with Nelson, Shankar, and Vladas, we actually showed that in models in this universality class, the degree and the page rank have very different tail behavior. So different centrality measures look very different. So in some sense, the result that I displayed to you today kind of points to that same thing, that somehow the global behavior, whenever you go beyond the one-step neighborhood, right? Whenever you go beyond degrees, it looks very different from what you see in static models. All right, and so the last thing I want to say is that the weak persistence that came as a byproduct of these calculations, so that also tells you that in models like the uniform attachment, suppose I gave you a snapshot of the network at time n and asked you, find the root, right? So in preferential attachment, you can use maximal degree vertices because they correlate strongly with the root. In uniform attachment, you can't because the maximal degree vertex could be very far away from the root. Now with this work, we know that, okay, so maximal degree can be far away, but the maximal components do correlate strongly with the older vertices. And that's how we hope we could kind of develop algorithms using sort of the centrality measures on components to identify roots. All right, that's it, right on time.
Thank you, Sayan. Time for questions.
Yeah, I have two questions. Like, initially started with the discrete time model, And then you said that, okay, the edges join at some random times. So does the same analysis also work for the discrete time? Because you can see it as like that discrete time process is embedded in the continuous time, or the techniques are only helpful for continuous time?
No, no. So that's why we keep switching between the two, right?
Okay.
So that is what continuous time gives you, the sort of independence. So these give you branching process approximations to these networks.
And
And then once you kind of track those stopping times where vertices arrive, that will kind of help you recover the discrete time.
the second question is like I do not understand like what is the significance of alpha pi that you wrote? Like I do not see them in the theorem. So like how are you using this alpha pi equation?
So remember this, right? So this goes to 0, right?
Yes.
So we get something like this, right?
Yeah.
Remember, S2 pi is the limit of the susceptibility, right?
Yeah.
So once you plug that number in here and compute this whole thing, this is your alpha pi.
Okay. Yeah. Thank you.
Hi. Yeah, thanks for the nice talk. For the general preferential attachment case, do you still get like these explicit formula for susceptibility, etc., or does it look?
Write that.
Is that?
Yeah, I didn't write that, but you do.
But it's not as nice, I'm guessing, is it?
It is at the same level of non-nicety as this.
Okay, cool.
Yeah.
Thanks.
Home team.
So the root finding, I find that very interesting. I realized that this is actually a little different from the usual root finding. I mean, there's a lot of work on root finding on trees, and there's beautiful work in that direction. But there you always have one random tree.
Mm-hmm.
Here, actually, we have a graph, and we make it a tree by percolating it.
Mm-hmm.
But then we could percolate it infinitely often. So it's like an annealed problem rather than a quenched problem.
Why do you say annealed?
Because you do your percolation on the graph that you get, right?
Oh, so
you could do it very many
you're
times.
looking at this jointly as a sample. Yeah?
Can you use that?
Good question. We'll think about it. I mean, the thing is, once you have anything tree-like, I mean, the heuristic is like you have some small loops, get rid of them, or keep percolating till you kind of get rid of them. And then you kind of apply your favorite centrality measure on those subtrees. And the details are here kind of hazy because what centrality measure, it could be just a degree, or it could be something like a centroid, like a rumor centrality or centroid or page rank. We don't know yet which one works. Many times, but even then you'll need some centrality measure, right? Yeah.
Any other question?
Is there a way to see this kind of behavior in random recursive trees, like the ones which Jean Bertrand and his collaborators
So
go ahead.
So random recursive trees are essentially m equal to 1 in this case, right?
Okay.
So it is uniform attachment with one edge, right?
One edge.
And then if you look at percolation, the root component is just a tree with a thinned out attachment probably, right? So in that case, the PageRank work will directly apply and give you a version of alpha pi for that.
So if there are no more questions, let's thank Shoyan again.